All right, fourth grade, your newest entry into your table of contents are 2 pages. 11 and 12 are my next available pages. And today we are doing Module 4, Lesson 13, and it's called Classifying Triangles. To classify means that you break things into categories and define them. So today we'll be doing those with different types of triangles. When you're ready, find your next 2 blank pages so we can begin. Today's objective is I can classify, I can categorize and define triangles based on their side lengths or their angles. Before we dive into different types of triangles, it's important to know what a triangle is in the first place. So we have our definition up here. A triangle is a shape that has 3 sides and 3 angles. And it's important that those 3 sides, 1, 2, 3, and those 3 angles, 1, 2, 3, close and form a closed shape. If we had any open sides or open angles, it would not be labeled as a triangle. You can see in front of you that you have 3 different triangles. We're going to make marks on these triangles and then name them. First, we're going to mark the equivalent side lengths. Go ahead and draw a box around the word equivalent because it's that important. Equivalent is a mathematician's term for equal. So looking at this triangle, we're going to mark the side lengths that are the same length. For example, in this first triangle, I noticed that these 3 side lengths are all the same length. To mark that they're all the same length, I'm going to draw a tick mark like this. Any side length that has this tick mark has the same length as the other sides with that same symbol on it. So by drawing these 3 tick marks, I'm saying that we have all equal sides. Now I'm going to mark the equivalent angles. Remember that your angles are the space that lie between your 2 sides where they meet at an endpoint. Just like the sides are equal, so are our angles. The space between these 2 sides are equivalent. These 2 sides, as well as these 2 sides. We have 3 angles, and they're all acute. Now I'm going to label my lines of symmetry. Lines of symmetry mean that if I fold that object in half, are both sides a mirror image of each other. Looking at this triangle and going up and down, I notice vertically, this side length, this side of my triangle is a mirror image to this side. I even have these tick marks to prove that both of these side lengths are the same length, so these are mirror images. Does the same work if I go horizontally? If I go side to side this way, the top half of my triangle comes to a point, while the bottom half of my triangle looks like a trapezoid, so that line of symmetry wouldn't work. What if I turned it diagonally? Any way that I turn my triangle so that this is the top point or so that this is the top point, I can still form that line of symmetry. Because I have all equal sides, as long as my line of symmetry begins at the point, I can fold my triangle in half diagonally this way. I can fold my triangle in half diagonally the other way. So let's name this triangle. What do we call a triangle that has all equal sides and all equal angles? Well, we call it equilateral. As you copy down that word, listen to your description of equilateral. Equilateral love peace. They love equality. They love things to be the same. In an equilateral triangle, all of your side lengths are the same. All of your angles are the same because they believe in equality. Classify this triangle by its angles. If we call this an equilateral triangle based off of its sides, what would we call a triangle that has these sorts of angles? I notice that every angle inside of this triangle is acute. How can I tell it's acute? Well, if I use a right angle tool and line it up, I can only see one line. The other line goes behind my note card. It's less than a right angle. It's less than 90 degrees. So this triangle would be acute. Let's take a look at this new triangle. It looks a little similar to our equilateral triangle, but you can tell it's much skinnier and it seems like it's been stretched up. Let's start by marking the sides that are the same length. I notice that this side length and this side length are identical, so I'll use my tick mark to identify that. But this side length is not identical. If I gave it the same tick mark, that would be like saying that these are all the same length, and that's not true. So to show that this is a different side length, I'm going to draw 2 tick marks like this to make it stand out. Now I'm going to mark my equivalent angles. I notice I have more acute angles. All of these angles are smaller than a right angle. But I do notice that this angle at the top is much scrawnier than the 2 angles below over here. So I'm only going to draw arches in my angles that are the same size. These 2 right here. Since this top angle doesn't match, we'll leave it blank for now. Now we're going to mark the lines of symmetry. First, I'll start by going vertically. If I go vertically, I know it'll be a mirror image because the side length is equal to this side length. This angle is equal to this angle. So if I cut my triangle in half going up and down, both sides are the same as one another. Horizontally, if I drew a line going across, I run into the same problem that I did over here. The top of my triangle forms a point, the bottom of my triangle forms a trapezoid, so we can't go side to side. What if I drew a line of symmetry going diagonally, like I did in my last triangle? If I followed the points of the triangle and traveled through, okay? Well, let's use my finger right here as a line of symmetry. They both form triangles, but these triangles are totally different sizes. This triangle has much larger side lengths, while this one has much shorter side lengths. So this line of symmetry wouldn't work. Same goes for this one. We have 2 different triangles, so it looks like our only line of symmetry would be traveling up and down. We only have one. We call this triangle isosceles. Isosceles. When you have a triangle with 2 side lengths that are identical, we name it isosceles. Take a moment to copy down that crazy name. And here's my trick for remembering this crazy name. I have 2 S's in isosceles, and I have 2 E's in isosceles. The 2 S's and the 2 E's remind me that I have 2 identical side lengths, while the next side length, the third, is not identical. So far here are tricks. Equilateral triangles believe in equality. Everyone gets the same side length. Isosceles triangles have 2 S's and 2 E's like the 2 equal side lengths that they have. So how would we classify this triangle by its angles? Just like in the last example, all of the angles inside of my triangle are less than a right angle. They're less than 90 degrees. If we have an acute angle inside of our triangle, it's called acute. Now let's move on to our third kind of triangle. Mark the equivalent side lengths, mark the equivalent angles, mark the lines of symmetry. This might be a little trickier than the other 2. Let's start by marking our equivalent side lengths. By looking at it, I can tell that this side length is going to be completely different than the other two. The other two might look close, so I'm even going to use a ruler to measure it. Okay, so this one's about 3.5 inches, and this one is a whole inch shorter. None of these side lengths are the same length as each other. So that would mean that we'd label one side with a tick mark. And since none of the other side lengths match it, I'll draw 2 tick marks on one of the other side lengths. And since none of the other ones match this one either, I'll draw 3 on my third side length. 1, 2, 3 to show that all 3 side lengths are different than one another. So what about my angles? Do I have any identical angles in here? If I use my right angle tool, I can see that both angles on this side are acute, but this one feels like a much skinnier acute than this one. They might both be acute, but they're not equivalent. They're not the same size acute angle. And over here, this angle right here is obtuse, I can tell, because it's larger than a right angle. It stretches past my right angle tool. So none of my angles are equivalent to each other. Which means when it comes time to mark my lines of symmetry, I'm going to have a hard time. If I go vertically, nope. Horizontally, nope. If I follow the endpoints of the triangle, nope. Nope. Oh, definitely not. This one's a mess. There are no lines of symmetry inside of this triangle. Do we know what we call this crazy triangle? We call it scalene. I want you to think of scalene like your crazy friend, Scalene, who's so unpredictable. Scalene, you never know what she's going to do next. She's got different side lengths. She can have different angles. She's got no lines of symmetry. That darn Scalene is crazy. Scalene, you never know what she's going to do next. So here's our tricks to remember so far. Equal, lateral, believes in equality. All 3 sides the same. Isosceles has 2 equal sides like the 2 S's and 2 E's in its name. And that darn Scalene, she is so crazy you can't predict any of her side lengths. They are all different than one another. So how would we classify this by its angles? Because you might notice we had acute angles, but we also had obtuse angles. There is no such thing as a triangle that has all obtuse angles. Because if it was all obtuse, it would be an open shape. We wouldn't be able to close it at 2 points. So since this triangle has at least one obtuse angle, we call it an obtuse triangle. Any triangle that has at least one obtuse angle becomes an obtuse triangle. Like so. So let's practice finding, locating, and naming some triangles as well. We're going to use the points that are inside of this grid to build 2 new triangles. They've already built a triangle for us called triangle IJK. When we label a triangle, we use the triangle symbol and the 3 letters of the 3 endpoints that connect together to form that triangle. Looking at this triangle, let's see if we have any side lengths that are equilateral. Well, I can tell that K and J and I and J are totally different side lengths. This one's about 1 inch. This one's a little less than 1 inch. None of these side lengths are the same. That means we draw 1 tick mark on one side length, 2 on the second, 3 on the third. Oh my goodness, 3 different side lengths. That is just crazy. You know what we call that? We call that our darn cousin Scalene. We can never guess what she is doing next. Let's label it now by its angle measurement. Let's switch our ruler out for our right angle tool. Okay. If I line this up, this is a little greater than a right angle, so this is not a right angle. And I can tell that the other 2 angles are obtuse. are acute. But I remember if I have at least one obtuse angle, we call it an obtuse triangle. Because we can't have all three be obtuse angles. If all three were obtuse angles, we wouldn't be able to close the triangle. They'd all be stretching in different directions. So now it's time for us to build our own triangles. I'm going to challenge you to make this triangle. Connect the letter G to the letter H. Connect the letter H to the letter C. Connect the letter C to the letter G. To name it, we draw a triangle symbol and the three letters that join it together. It doesn't matter which letter we start at. We could call it GHC. We could call it CGH. We could call it HCG, as long as we have those three letters to show that it's together in one triangle. So now let's check our side lengths on this one. Okay, this is about 2 inches. 2 1/4 and 1 1/4. They're all different. Oh, you guys know what happens when they're all different. First, we label them with their different tick marks like so, and they are so crazy. We can't predict these side lengths. Again, we have our friend Scalene, who's here. Now let's talk about the angles in here. I'm going to pull out my right angle tool again. I can spot pretty quickly that in the corner of this triangle, it lines up perfectly with my right angle tool. This is a 90-degree right angle. Since this lines up with my right angle tool, we call this a right angle triangle. That's what we would classify it by, as angle measurements. There's no such thing as a triangle where every angle is going to be a right angle. That would just form an open square. We're going to need some acute angles to close the triangle, but since we have at least one right angle in there, we're going to call this a right triangle. Let's practice one more. We're going to connect A to B, B to D, D to A. Remember to name it. You draw your triangle symbol and the three letters that work together to form that triangle. If I look at my triangle, and I can even see it using my grids, I notice that it takes 1, 2, 3, 4 boxes. 1, 2, 3, 4 boxes, and I can even use my ruler to measure the side lengths here. These all look to be about the same side length. It is, they're each 1 inch. So that means they each get the same tick mark to show that they're all the same side length. What do we call a triangle that believes in equality? Everything is equal. Well, those are our equilateral triangles. What kind of angles do we have in this triangle? If I use my right angle tool, I notice that no matter the angle I frame it towards, they're all smaller than my right angle. When all three of my angles are smaller than a right angle, if all three angles are acute, I call this an acute triangle. Before you wrap up your lesson today, turn to the people in your group with you, and I challenge you to look at this triangle. E, F, and G. Together, can you guys decide what type of side lengths we would classify this with, and what type of angle measurements we would classify this as well? Then we'll come together as a class and decide what we would call this. When you finish having those classroom discussions, take a picture of your notes for Seesaw and move on to your problem set.